positive photoresist means area exposed to light gets dissolved in developer. Okay, that is called as positive photoresist. Positive PR. Negative PR is vice versa. So that area which is not exposed to light gets dissolved. Okay. So when we are ordering mask designer, right? So we need to say that what we have. Are we going to use positive photoresist or negative photoresist? If we are using positive photoresist, the mask designer will make those areas clear where we want to have metal there or where we want to do the fabrication. Okay. And if it is negative, then it will be vice versa. The mask maker will make those areas dark where we want to access. Okay, we can access that area for fabric deposition. We can access that area for doping, right? Or we can access that area for etching also. Sometimes you need to do etching. What is etching? So this is the wafer, and I want this area to be etched. So I need to make a mask, right, to have access to that area. So I will do the photoresist step and then development step. So it may look like this. Right, this is photoresist. And now I have this area. Now I want to etch this. So what I will be using, I can use HF, hydrofluoric acid. So this is called as wet etching. I will just put the acid there, or I can do dry etching. So in dry etching, I may use plasma and then scrape off that area. So in the next step, how it may look like. It will look like this after the lift off process, right? So when we are etching, the photoresist may also etch, but the thickness of photoresist should be 3 times more than the depth which we want the etch, right? So if we want a depth of or a hole, right, or we want to dig for 100 nanometer, the photoresist should be 300 nanometer or above, right? So what else we have done in the last class? So this concept of fabrication, this concept of doping, we have discussed, and then concept of aligners, right? How do we do the exposure of UV light, and then we said what is development, right? How to develop. Then we talked about deposition, sputtering, and evaporation. And then we said that after that we do the lift off process. Okay. And doping has 2 methods, oxidation has 2 methods. Okay. So today we will start with some videos and then continue the lecture. Is it? Yeah, so we need to do the exposure for certain time, right? So that will go deeper and we have to clear off that area completely. Then we get selective access on the wafer, right? What's that? Depth of time. Again, time. So you put it for 1 minute, this much etching. So 4 minutes, then that much etching. So that's where the process engineers, right, help us. But we have to become our own fabricator. When we are fabricator, we have to study some chemistry, some physics to understand what is the reaction happening. They're all chemical reaction, right? When the acid meets the photoresist, it will dissolve this, and the byproducts are this. That kind of process is happening. So this guy is explaining his own process. Like he want to oxidize first the whole complete layer, and then want to. That is a good procedure, because we are now on the silicon. We first cover it everything with oxidized layer so that our wafer is saved now. Whatever we want, we can selectively etch and then use those areas. Are you able to hear him? I don't know where is this people. That sound I don't know how to control. Do they have to increase it from there, or? But anyway, I will explain otherwise. That person should increase sound. I don't know where is that person. But if I am talking, are you able to hear me? Backbench? Okay. Let's give a missed call. మీరు కాల్ చేస్తున్న వ్యక్తి వేరే కాల్లో So this is the spin coater. This in detail he is explaining. Okay, the steps are you able to understand, right? He has done the spinning process. Total, I think he is talking about that spin coating only, right? His life is around spinner. Yeah. Development of SU8. Yeah, this is the exact thing in reality happened. That hood, it's chemical hood. It will take away any fumes which are coming out, so it will not be harmful for you. You are covered with that glass. You will be watching through that glass, and all these chemicals will be exactly located where he is talking about. Okay. So he is doing the development which we have discussed, right? You see that he took the beaker and put that. He is explaining in detail disposal of waste, everything, right? I think this video I kept it to give you a feel of what really happens, right? Okay. 25 minutes video, so we can't spend 25 minutes, right? Yeah, here I kept it 2 to 5 minutes. 2 to 5 minutes. So this video we have to see from 2 minutes to 5 minutes. This is deposition. So when she is saying lacquer, it's nothing but photoresist. This is photoresist, right? Doping, right? He's making a transistor, right? You can understand. Yeah? Okay. So she is talking about like for her, for this company, the supplier will be wafers, right? That's what. So for ion implantation, ion implantation. Yeah. This is how they accelerate the ions, right? Through these. The beam which comes out. Okay, that's it. These videos are to give you the visualization to what we have discussed. So what does it mean if I want to put p-type, right, inside the silicon wafer? What I need to do? I need to put that in a chamber and create the concentration of surrounding so much that it should feel that the concentration which is in the chamber is high than the silicon, then it will go, right? So therefore I need to cover the remaining areas. I cannot selectively do it. So here again, diffusion will depends on time and this rate of diffusion, right? This is sputtering. CVD is nothing but chemical vapor deposition. The concept is arrangement of deposition is similar. Okay. Like here, Gone. Okay. One procedure we can see it from CVD. This is like we are releasing chemical vapors, and in presence of pressure and temperature, reactions are happening. What we want is getting deposited. What we don't want is getting evacuated from that pump. So you got a picture, na? Everything. Let's go towards packaging. So packaging is so when we see the wafer from the top, right from the top, how do we make the connections, right? Like if we are saying there is a interconnect, which is connecting one device to another device. And in this box, we have, let's say, transistor. So to transistor, we have seen that we need access point. So this drain, gate, source, these things will come out on the top layer, let's say, and will look like this. So a metal coming out from gate, drain, source. These are nothing but some metals, right? Interconnects, which got connected below, right? And they came out as a strip. Now these wires or interconnects are connected to something called as pads or pins. Okay, these are standard sizes, 75 mm by 75 mm, 150 by 150, or 200 by 200 micrometer. Okay, so these pads are now sitting on your wafer, ready to be connected to the outside world. How do I make this connection? Right? So from where what kind of connection do we give to these devices? Let's say if it is a transistor, right? So for to gate, I want to give some input. To drain, I want to give some VDD, supply voltage. Supply voltage, where will I get from? Either I can get that from battery, or I can make a power supply, right? So you started the lab, I think first lab has done it the last lab. You have seen the power supply, right? So that's a DC power supply. So you want to give that DC power supply, that is called as VDD, to your drain of your transistor. And similarly, source of the transistor has to be given to the ground. So that means two wires comes out from your power supply, or two leads or two connections will come out from your battery, which has to be connected to your drain and source. And then input, from where will you give? You have seen a function generator in the lab, right? Function generator is nothing but it is generating some functions. What type of functions? Square wave, triangular wave, sinusoidal wave. How to generate that you will study in some courses, right? So you will be getting those signals that will be given to your input, right? So now how do you connect this VLSI to the outside world? Because these are nothing but pads or pins sitting on a platform. So what you do is this pad, solder it with one wire and pull that wire and connect it to pin of your IC. Okay. Then another will come out like this, another will come out like this, another will come out. So you will get pins. So those ICs which you take it and press that into the breadboard, or the same ICs which goes and sit on your PCBs. PCBs are nothing but green color one which we see it in our computer, right? So it will have holes. If you want to fix a 6-pin IC like this, 1, 2, 3, 4, 5, 6. Then there will be 6 holes there on the PCB. You press it in those holes. These pins comes out and will be seen from the back side. Then you can do soldering to connect it to other set, right? Other parts of your board. So these pins are nothing but which are letting you connect to the outside world, right? So inside what's happening, this is what happening. To the wafer, we are doing some soldering. So they are called as bonding, okay? Wire bonding. So when you do packaging, you do wire bonding. So you connect it. Gold wires, usually gold wires are used to connect the PCB to the IC, not IC, silicon wafer, right? It is soldered and then connected to the pins. Then you cover that pin. Okay. There are other kind of packaging also. What you do is all these things wherever pads are there on the chip, you connect something called as ball. You will have another packaging material which will have raised balls. So they will just come and sit exactly on the pads. So you put those raised balls in such a way that they match the alignment in such it will come and sit on those pads where you have the connection. So this kind of packaging is called as flip chip packaging. Okay. So to see how to visualize that, we can see a video on that packaging. Again, they are using vacuum to hold it tightly, the wafer. They want to cover the wafer with some film so that other areas does not get affected. So there are two ways of packaging. This is one way where we are telling the customer that the fabricator that don't package it with the IC pack. I will do the measurements by using a probe station. So we have in triple IT also one probe station. So what we can do there is we can directly connect on the wafer and do measurements. Okay, we take a pin and connect directly on the let's say from power supply, we take two pins, one on the gate and one on the drain and one on the source. Then we take out one pin from function generator and put it on the gate side, right? That kind of packaging. So at that time, we don't want them to do those bindings, wire bonding, and all those things, because the pricing of packaging with wire bonding and then IC flip chip, whatever, is equal to that of fabrication. So in order to save money, what we can do is we buy one-time probe station and then we ask them to package like this and give it to us. Then we can probe in directly. We scrape a little bit and access on the pads, right? The other packaging may be here. Okay, let's see this video. So this Quick Pack is a company. They are advertising their business, right? We have one in Bangalore also, packaging industry. So until we give some powers, we can always put water or acetone on that, no problem. Even if it is ready fabricated one. Unless we do a good drying, right? Wire bond. This is how the wire bonding is done. So what you can see that wire bonds right now. This is flip chip assembly. This is advertisement. We can do 10 nanometer also. That's what they are saying, right? I think they privatize their link, I think. Okay. Yeah, that's it. So clear, na? Packaging part is it. All right. Let's continue our discussion now. Layout design.